Okay, we're live. And for those of you watching this recording, this is a rare experience, a rare treat, because this lecture is actually being given live. I actually have people in the room. As you know, I'm used to lecturing to empty tables and empty chairs, but now I have an exciting group of people. Everybody wave to the camera. Look at all the people. The classroom is full to bursting. So now you guys are immortalized. For the next 40 years, all of my 115 classes will see you guys. And when you guys are in your 60s, the video of you in your 20s will still be available. Post it up on YouTube. Okay. The topic for this recording is the shape of magnetic fields. So magnetic fields are vector fields like the electric field, and remember that the magnetic field is created and caused by electric currents. There's still a mystery hanging around about how do we get magnetic field, how do we get so-called permanent magnets, you know, the little refrigerator magnets and things like that that don't have currents anywhere, or at least no currents that are visible. So where do those magnetic fields where do those magnetic fields come from? And in fact, I will answer that question in due course. But for the time being, let's focus our attention on just magnetic fields that come from currents. By the way, to give you a heads up, the answer is going to be that even permanent magnets, refrigerator magnets, solid magnets, those things are also caused by electric currents, as it turns out, even though there aren't any currents obviously available. But they are there. In any case, so let's not worry about that right now. For now, let's think about the magnetic field you get by running a current through a wire. And as was true with electric fields, remember my strategy with electric fields, which I always started by examining the simplest possible source charge I could come up with, which was for electric field is just a point charge. I'm going to employ a similar strategy for magnetic fields. And the simplest possible source current for a magnetic field is a long straight wire. Okay, and you presumptively are comfortable with what I mean by long now. An infinitely long wire, what it really means is that the distance at which I'm calculating or measuring the magnetic field is small compared to the length of the wire. So this wire is, about 80 centimeters or so. And so if I measured the magnetic field at 1 centimeter from the wire, so we're like really close to it, then to a really good approximation, we can treat this wire as essentially infinitely long. Is that okay? We're just good with that, okay. And the next assumption we're going to make, which is actually, in this case, this is a really good assumption. In fact, it's almost always a completely perfect assumption, and that is that the current that we are running through it is constant, both in distribution in the wire, and more importantly, it's constant in time. In other words, it doesn't change from moment to moment. Okay, so with those two assumptions, I'll draw. I didn't have any blue. I would have chosen a blue wire, but I don't have any blue wires. The reason I want blue is because we are still assuming our conventional charge carriers, which are positive, right? So our current is running through it. Okay. And so anyway, the question now is, what does the magnetic field of this thing look like? The answer is not obvious, not easy. It's not incredibly difficult either, but it's certainly not obvious. But the hint of what this magnetic field might look like comes from, you remember I've talked about the reason that we think of this or know that the field that we've created is in fact a magnetic field is because we see that magnetic compasses are affected by whatever this field is that the current is producing. So that's our evidence that we have a magnetic field. And more than that, we can use a compass, which unfortunately I don't have any compasses with me, but you all know what a compass looks like. Yeah, you all, okay. So you can imagine I have a compass in my hand. And what happens is if I point the compass or bring the compass near this wire as it's carrying its current, I'll see that the compass needle is affected, but what I'll discover is that the compass needle does not point parallel to the wire, but in fact it always points in a direction perpendicular to the wire, right? So if I brought a compass needle around here, so bring a compass and I put a compass there, my compass needle would end up pointing like that. The north pole of my compass needle would go like that. Okay. And then so that's the north pole, and then this would be the south pole of our compass needle. My point being that, well, and then we say this, and if I were to then move my compass around the wire, I would find that the compass needle would continually rotate as I rotated around the wire, so that the compass needle is always pointing perpendicular to the current. So it doesn't point parallel to the current, it points perpendicular to it. So I spend the next 2 hours slowly and carefully moving my compass needle around my wire, near my wire, closer to it, further away from it, and I use it. I use the way the compass needle deflects, because after all, if the compass needle is deflecting, it must be experiencing a force, right? Okay. So anyway, I use it to map out the magnetic field that's causing this force, and I eventually discover, without going into excessive, unnecessary detail, I eventually discover that the magnetic field of this wire does not point toward the wire. The magnetic field doesn't point away from the wire. Rather, and this is the peculiar part, the magnetic field forms closed loops that circle around the wire. So if my wire is like this, right, then my current then forms a circle, and watch this. I need 3 hands. Okay, no. I'm gonna have to give you a hand. You can avoid being on camera if you want, or you can lean in and say hi. There you are. That's Madeline. It's Madeline, right? Maria. It's Maria. Who's Madeline? You're Madeline. You want to come up and say hi? Okay. All right. Anyway, so if my current is flowing towards Maria, I'm really bad with names, by the way. If my current is flowing that direction, what I discover is that the magnetic field loops are forming closed circles. They don't touch the wire. They don't start at the wire. They don't end at the wire. They circle around the wire and everywhere. So there's one there. There's one there. Closed loops. There's one here. All the way around. A continuous field. They're not just little rings. It's a continuous field. But the direction, what's really happening is that the magnetic field lines. Do you remember we drew electric field lines back in the day? And what I said about the direction of the magnetic field, the direction of the electric field vector at any point on an electric field line. Do you remember what I said? Tangent, right, exactly. That the magnetic field, the electric field vectors were everywhere tangent to the electric field lines, right? The electric field lines are all curvy and stuff. It's exactly the same concept here. Our magnetic field lines are curved, closed circles around this long straight wire. At any single location in space, the magnetic field vector is tangent to that closed circle. Question so far? Which is not, by the way, something I get to say in most of my recordings. I never get to ask for questions. No, keep holding it. There you go. No questions so far. Okay. Now, the next issue is that the magnetic field, being a vector, has a direction. So obviously we got to worry about the magnitude and the direction. Okay, let's do the direction first. The direction, of course, circling around the wire. The direction, it could be circling like this, so going towards the camera, towards you, at the top and then coming around away from you at the bottom, or the reverse, right? I could be going this way. And the question is, which is it? And once again, we turn to experimental evidence. We look at what the compass needle does. We look at what the compass needle does to map that out, and the answer turns out to be that if the current is flowing that direction, okay, towards Maria, then the magnetic field vectors are circling around in this sense, that they're going toward you above the wire, they go down in front, away from you at the bottom, and then up, so like that, okay? And if the current gets reversed, if the current were to flow this direction instead, we would find, unsurprisingly perhaps, that the direction of the magnetic field vectors also reverses, and so it would go the other way, okay? And so how do you keep that straight? The right-hand rule, okay? And here's an application of it. What you do is you grab the wire. Here's how you work it out. You grab the wire with your right hand, with your right thumb pointing in the direction of the positive conventional current flow. Okay? And then your finger, and then grab the wire, and then your fingers automatically curl around the wire in the same sense that the magnetic field vectors curl around. Okay? And if the current reverses direction, okay? She's camera shy. If the current reverses direction, so now it's flowing that way, right? Then you apply the same rule. You still grab the wire with your right hand, right thumb pointing in the direction of the conventional current, positive current, and then your fingers curl around. Okay? And so wherever you want to determine the direction of the field, you simply put your fingers there. So if I want to know the direction of the field up at the top, I simply put my fingers up at the top and let my fingers curl around. Making sense? Okay. Now, yeah, I think I'll, okay, thank you, Maria. You're well done. Okay. Now, yeah. So the question was, does that mean that the magnetic field lines have direction so they're not scalar? And that's exactly correct. Yes, the magnetic field lines are vectors just like the electric field lines were. Yep, and you've got to put arrowheads on them as well. And in fact, here goes the directions. So I guess I'll draw them, I guess I'll just draw them in brown, I suppose. Let me get rid of my compass here. So here's how you draw a magnetic field that's circling around a wire. Here's how you draw it in 2 dimensions on a whiteboard like this. Okay, so I'm going to do the same thing. Only I'm just going to lower this down so I can reach it more easily. Okay, so again, with the palm of your right hand, grab the wire. So now you have to be imaginative. But you grab the wire and let your fingers curl around like so. So you'll notice that doing this with having drawn the current pointing that direction, again, positive current, everybody, positive current. Then my fingers are coming out of the board above the wire. They're curling into the board below. And so, and that's true everywhere along this long straight wire. And so my magnetic field vectors are going into the board below and out of the board above, and this is how you would represent that. Okay? Does that make some kind of sense? Okay. And in just a moment, I'm going to give you the mathematical expression for calculating the magnitude of this thing. Well, actually, let me go ahead and do that now. No, I'll do it in a moment. Because this is the side view. This is the wire like that. If, on the other hand, if I wanted to show you an end view of the same wire, okay, let's have the wire, I'm sorry, let's have the current flowing into the board. Still positive current flowing into the board, okay? And I want to draw the magnetic field vectors. Okay, they're going to be closed curves. So you do the same thing with the palm, with your right hand, grab the wire, grab the current with your thumb pointing in the direction of the positive current flow, and your fingers curl around the wire like so, right? And I only have a couple more minutes, but that's all I'm going to need. Okay, so my current is flowing that way, and so my magnetic field vector is a closed circle, and it points like that. Okay. So these two are exactly the same drawing. I've just drawn them. I've just rotated the drawing by 90 degrees. Okay. A thing you can and should practice at home: reverse it so the current is coming out of the board, and draw the field line like that. Okay. But there's one other thing I want to show you before this recording ends. That's the direction for the magnetic field. As for the magnitude, the ICVS. Have I done ICVS with you? Yeah, it can be shown. Right. So it's really complicated to actually derive this calculation, and it wouldn't be terribly enlightening for you. So I'll simply hand you a result. The answer is that the magnetic field can be calculated as mu naught times I over 2 pi r, where I obviously is the current that's creating the magnetic field. Mu naught is the magnetic field constant we've talked about before, 4 pi times 10 to the minus 7th, right? And r is, well, what do you think r is? Physically, what distance? From the wire to, there's no source charge here. From the wire to, what am I calculating? Magnitude of magnetic field. So R would be the distance from the current to, what was R when I did electric fields? Distance from the source charge to where? The point of interest. The location in space where you're calculating the field. Same thing here. So R is the distance from the wire to the point in space where I'm calculating the field. Okay? And that means that the magnetic field is different at different locations, and so B is in fact a function of R. And so this is for long straight wire. Okay, one last point, and then I'll shut this down. Since the magnetic field is a function of R, notice that the magnetic field gets weaker as you get farther and farther away from the current, which sounds reasonable, doesn't it? The farther away from you are from the wire, the weaker the field should become, which means that drawing in cross-section here, I would draw the field like this, except actually let me make a nice, slightly better drawing here. So my current is going into the board, then I would draw my field like this. And two things. One, by the right-hand rule, my magnetic field lines curl around. They all curl around in the same sense. And the other thing I want you to notice is that the field line density gets smaller as you get farther away from the source current. It's exactly the same thing we did with electric field lines. The strength of the field is indicated by how densely packed the field lines are. And so the drawing here is a reflection of the 1 over r dependence of the magnetic field on distance. Questions? Okay, so in the next recording, then we'll talk about the magnetic field of a circular current loop, and it's going to be very similar to this with a lot of the same considerations, but there will, of course, be some subtle differences, and that'll be the next recording. Oh, and all of you watching the recording, you should applaud the people here in the room. That was very